do. So I found these paper. It's not a paper, it's actually a thesis that yeah, so that basically goes through hypergraph states. But like that's the standard definition of hypergraph states. This means the states that are like there's a bunch of a lot of introduction in here. Um, quantum competition, quantum circuits, gets this correction, multiple graph states. So I think this is where we should focus on. So this whole thing with graph states and hypergraph states, and this is basically the definition here, right? It's a bit different than what I'm trying to do, but I thought it might be just good because that's a really well developed concept, and I real in these theses there is some actual there's actually some kind of transformation concept defined on top of these, right? Where we have a graph state and then you define a transform that, kind of would be equivalent to a gate, I guess, and then they go and build it as a sort of a transformation of the graph or the hypergraph. And so I wanted to kind of go through these because at the end of the day, if you so if you stay with what I'm currently working on, the way that I'm currently setting it up, it almost doesn't feel like that's the give me a second. So that definitely it's not. It almost feels like, as I said, working with a wave function still, right? In a sense, like you have the same problem with where the hell is the Twitch app? There you go. Oh, wait a second. I can just tweet it. I can just tweet these. Twitch.tv slash oh, come on. Uncertainties, I think it is, right? Uncertain cis. Show me while reading about graph and hypergraph states. Just reading about hypergraph. Yeah, there you go. So basically, the way this works is if you have a graph that is like this, right? You have like, this is qubit 1, 2, and 3, and you have a graph that looks like this. So the way you read this graph is by kind of like, or the way the equivalence to the circle would be Hadamard, like each node is a qubit, and you put a Hadamard to each node, and then the edges in this case are translated to control Z gates. So this would be a Z gate, and then this would be another Z gate. And yeah, I mean, I guess the idea is that's so what this guarantees is that every edge actually represents like a sort of a pure entanglement, right? Because that's what you get with the control Z combined this way. essentially you have so you have this kind of maximum entanglement. Yeah. So that's what you get with these, right? And so the hypergraph version of these is the same, but like with multi-control Z gates, I think. So hypergraph states correspond to mathematical structures of hypergraphs, generalizations of hypergraph states is locally maximally entangleable states. Locally maximally. So this means that, that locally, so like the qubits that are entangled, they're always maximally entangled, right? So you construct them by a hypergraph states constructed in a manner. So for each vertex, we initialize the physical system with a +1 eigenstate of the Pauli X operator. So that's the plus state. So that's just a Hadamard gate. Yeah. And for each hyperedge, we calculate edge cardinality, and we apply an E-qubit entangling unitary represented by the diagonal gate C on the qubits in the hyperedge initial state. As a result, we get a hypergraph state responding to hypergraph move. So in CE, it gets generalized CZ gates, yeah. So the simplest non-trivial example of hypergraph state that corresponds to a 3-vertex hypergraph is an hypergraph containing all 3 vertices. Yeah, so that would be the simplest here, right? So that'll be the circuit to do that. Cool. So now I'm interested to know. So this is page 44, and now I'm interested to know how do they define. So there's a bunch of things in here that I've seen. Local Pauli equivalences of hypergraph states. Let's take a look at these. And then there is extreme violation of local realism quantum hypergraph states. The non-local properties of quantum hypergraph states. Not so much interested into these. I'm interested into the general multiparticle non-locality. I'm currently interested into and the graphical transformations. And I think that comes later. Yeah, there you go. Graphical rules for transformations and hypergraph states. So let's try to understand these first, maybe. Okay, so what do we have here? And the thing is, I just probably want to use that as a see if I get any inspiration for the stuff that I'm trying to do, because I'm trying to do a bit of a more generic thing than these, right? So I'm trying to say, that I kind of have a generic situation where I want to be able to tell more about the correlations. That's the way I want to model entanglement. That just the graph states and hypergraph states model a really small subset of it, right? So I want to be able to say, look, there is, like, if I just use an edge, Like, or even say just for a simple graph like these, right? Hypergraph. So the simplest one that I could think of. Like that can mean many things, right? And I wanna be able to represent in a way every possible state, right? So I want this to tell me more information than, the hypergraph definition of these would be, well, that's what that's the state that you get if you apply a Hadamard gate to the qubits and then a control Z. I guess the reason the control Z is used is because it really doesn't matter. It really doesn't matter, what qubit is what, like where the control is, and so these hyperjs are not directed in any way. All right. But I'm more keen to say, like let's imagine I have a qubit in here, and I'd like to define the state as, something that lives in the hyperedge, and say that's state 0. I could also use another ring, sort of another hyperedge, to specify that maybe that's a mixed state, right? Versus having like the pure plus state in here, for example, right? So this so you go and define the hyperedge as in containing a potential state of the system that it encloses. This means if I have two qubits and I draw a hyperedge around them, this hyperedge can contain, or should contain, a possible basis state. No, no, not a possible basis state, a possible state of the system, right? Maybe the system is, maybe this system of two qubits, right? That's a good point. That's a good point, because I'm all the time stuck with, by saying that, for example, I would represent the Bell state like this with two hyperedges, right? But then on the other end, that is that is in a way wrong, right? Because if I define things like these, then why don't I define the Bell state like these? Why don't I do this like that? That's a good question. Like if this is mixed, right, and this is pure, I like this because essentially you're treating, okay, let's put it like this. it's maybe not the state that the system is enclosing, but it's rather you still wanna try to keep you still keep trying to keep track of what the values of each qubit. Yeah. That's why this makes no sense. That's why these make sense, because essentially what you have is you have this state here. So it's like almost like, you have the 4 data points, like, or the 2 data points per edge in this case, because it encloses 2 qubits. So you have these and these, which is more accurate, because then you're saying that the state of this qubit is kind of spread across 2 different hyperedges. And so it behaves like if it was a mixed state, which is what we want the model to represent at the end of the day. Right? And that is fair. And I think that way of modeling just makes sense. What I don't know if it makes sense or not is, no, what I don't know is just I don't know how to operate on these. I don't know how to evolve these, because my intuition is telling me that, and that is just still the wave function intuition. Um, how do I go from these, right? So this is let's imagine this is my state, right? And how do I go from these to say, well, now I apply a control X and I get exactly that, right? So I get that. I'm going to do it like that now, because so how do I go about these? We can draw it like that, right? Because that's what we want the control X to do. That's what we want the control X to do. So I thought maybe I'd kind of try to get some inspiration here. But let's see. So here we've got some examples of operations. Let's try to see if these things make sense. So hypergraph states form an interesting family of multi-particle quantum states and have an insightful graphical representation. In this chapter, we give a collection of transformations of hypergraph states, which also have a nice graphical rule. Such actions include local and non-local unitary transformations between hypergraph states. This leads to a generalization of local complementation and graphical rules for various gates, such as the CNOT gate and the Toffler gate. As an application, we show that already for 5 qubits, local Pauli operations are not sufficient to check local. So local Pauli operations are not sufficient to check local equivalents of hypergraph states. Next, we study Pauli basis measurement rules for hypergraph states. For Pauli Z, this rule is rather simple, and it was given in reference 103. We give a sufficient criteria when Pauli X measurements do not have hypergraph state space. Do not leave hypergraph state space. Multipartite quantum states, known as hypergraph states, generalize several features of graph states. First, they meet the stabilizer description. They also violate local realism exponentially. Whatever that means, something to come back to, I guess. Most relevantly for this chapter, they have nice graphical rules for Pauli equivalences. Since different graphs and hypergraphs may lead to quantum states with the same entanglement properties, it is important to study the action of local and non-local unitary transformations between these states. For graph states, the local complementation plays a very important role. Physically, this map is implemented by local unitaries, which correspond to the square roots of a local Pauli stabilizer. Likewise, we derive the graphical rule for the action of the square roots of a non-local stabilizer. The unitaries obtained this way are not necessarily local, but give several constructions for which one can manage and to restrict these operations to local Clifford transformations. So this is an example. Generalized local complementation transformation T1 is applied to hypergraph A. The adjacency of the vertex 1 is A1. So 2, 3, and then 4, 5, 6. As a result, a new hyperedge is added to the hypergraph. Since the hypergraph states are equally weighted, Boolean function encoded states as defined in transposing some of the computational basis elements map hypergraph states to hypergraph states. What? Transposing some of the computational basis elements map hypergraph states to hypergraph states. Does the sentence make sense? Pauli X operation is the simplest such transformation. We express general transposition in the form of multi-qubit controlled Sinon unitaries and derive graphical rules for hypergraph states. These rules find applications in several directions of quantum information theory. First, they are one of the core transformations when deriving entanglement witnesses for hypergraph states. Second, they are used when deriving graphical rules for Pauli X basis measurements, which are themselves crucial to construct measurement-based quantum computation protocols. To sum up, this is a new graphical rules of states. Yeah. So, what is local complementation? We introduce the concept of local edge pair complementation hypergraphs around a vertex A. Let us define first the set of adjacency pairs of vertex A to be the set of A1, A2, where A1 does not equal A2 and A1 belongs to A1 and A2 belongs to A1. Of all distinct pairs in the adjacency set, to be the set of all distinct pairs in the adjacency set. The local, so this is the local edge pair complementation, okay, the adjacency pairs of vertex A. So you take vertex A, and then all vertex A, so it would be 4, 5, 4, 6, 5, 6. So all different pairs. The local edge pair complementation on the vertex A complements the edges in the multiset P. Notice that P is a multiset and only the edges appearing with odd multiplicity are be affected. Complementation of the edges in the multiset means that they are deleted from the hypergraph if they were already present, and they are added if they were not present. The local complementation or local edge pair complementation is implemented over some vertex A of a hypergraph H by applying the square roots of the stabilizer HA. Note in the sense that the square roots have to be chosen in a particular way. So this is the local Clifford equivalence of two application of two local Clifford operators which effectively implement two local complementations over vertices 1 and 5. Importantly, the signs of local complementations shall be chosen to be different from one another. These two maps commute and moreover square roots of adjacent operators on Qsaid cancel out. Oh, I don't really know. These two maps commute and moreover square roots of adjacent operators on Qsaid cancel out. So this is adjacent. These are adjacent, and so. So for any hypergraph state corresponding to a hypergraph H, the transformation tau A around vertex A performs a local edge pair complementation and its corresponding hypergraph. Note that the transformation tau is a non-local map, so it can change entanglement properties of the state. The name generalized local complementation should not be interpreted as if the map is local. For example, for an example of generalized local complementation, see figures 4.2. We said that the 4-qubit hypergraph states Pauli operators are generally insufficient to describe local integer equivalences. We investigate local Clifford operations, interactions, and hypergraph states. It appears that one can take advantage of the generalized local implementation rule by applying it over different vertices in the way that all the non-local interactions cancel out. Then a new hypergraph state is obtained as a result of local Clifford operations. To give an example, consider the 5-vertex hypergraph with hyperedges, blah, 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 blah. Then one can write explicitly that the local completion over the vertex 1 can be implemented by several local Clifford gates. So I think I get that. What this does is it just takes, say, all the possible pairs of like adjacencies, and then it creates or deletes edges. I mean, all the possible pairs. I'd say all possible subsets, right? Because here's our sets is like 1. So for the outer hyper edge, there are 3, and so that's why we're adding like a big hyper edge in here. And then from this hyper edge, like 1 to 4, there's a 2 and 4 that get also an additional line in between. I can open some line maybe this way. Let's take that simple example here, right? Okay, so let's try to build that. So we have 4 qubits. So we have 4 qubits, right? We have 4 qubits, and so we do, we do these, right? And then there's a hyper edge between 1, 2, 3, and 4. So there's like a, these, right? And then there's the 1, 2, and 4. So 1, 2, and 4. So that's the state that we have. So that's a state where only, so it's an equal superposition, and then only one element has a negative phase. And now what happens if I apply next gate here? All it does is move that to this state, where this is the one that's got the negative phase. And now let's try to construct this one here. That will be trippy if that works, right? Because that is basically telling me that on top of these I have between 2 and 4, 2 and 4. Okay, now I gotta correct for this one. Whoa, that is actually working, man. 2, 3. No way. Okay, cool. That's interesting. Fuck. That is cool though. So a next gate in this case is this local complementation thing. How the fuck did that come? Did they come out with these, man? It's pretty nuts. But I get it. So these only works, right? Because we're working on a really specific subset of like well, in a way. in a way, what an next gate does is just flip. In this case, right? It's just flip a state, right? Like you can just think of, you know, just flipping these two states, right? Okay, but and so I'm looking for something like these, right? I'm looking for something like these where maybe not like that, but something that you can, yeah, something like these. Oh, that looks so shitty. That's like a creepy face. Hmm. Like, you know, so that's the bell state, right? Essentially, essentially that is kind of impossible, I think, to generalize like that. Graphical rules for permutation integers and hypergraph states. Yeah, so this is the, and now comes the C-naught stuff, right? So this is what the C-naught is doing. So in the previous section, we considered the extension of local complementation for hypergraph states. In this section, we investigate different family of unit transformations. We call them permutation unitaries. These transformations permute the vectors of the computational basis. Such permutations are obviously unitary, and it's clear that they map hypergraph states to hypergraph states, so there must be a graphical description. The simplest example of such permutation is the Pauli X or NOT gate, action of which was studied before. A non-local example of a permutation unitary is a C-naught gate. This is a non-symmetric gate in its input, so one has to clarify which qubit is controlled qubit and which is the target one. Its extension to 3 qubits is the Toffoli gate. The Toffoli gate is itself conjugated CCZ. So, okay, clearly it is not necessary to consider all permutations, as any permutation can be viewed as a sequence of transpositions. For 2-qubit permutations, one can easily see that NOT and C-naught are enough to cover all possible permutations. Additionally, it is known that every permutation can be realized by means of a reversible circuit using the NOT, C-naught, and CC-naught basis. A most one in Sylvia, it's possible to derive a graphical rule of how such maps transform hypergraph states. Here we give the rules explicitly only for the 2-qubit C-naught and its multi-qubit extensions, but the methodology can be applied to derive any arbitrary permutation unitary if the exact graphical transformation is needed. Now, what I'm also getting at is that the hypergraph states, like, you won't be able to map any operation to a graphical transformation, right? Because essentially you would be like, say the controls that you would actually change, you could actually destroy entanglement, and so you would get your hypergraph into a state that it's outside of the hypergraph states space. So applying a C-naught gate on hypergraph state, where C is a control and T is a control, introduces the least hypergraphs of the hyperedges of the form ET united with C, where ET is the adjacency of the target. Okay. Okay. So we add the control to all the adjacent elements of the target. So that's what's happening here. So we're controlling one like C naught here. So we're adding the hyper edge among all the adjacents of 2. Oh, wow. Okay. What about we try this? So again, clear circuit, and so we have 9 qubits. And we have like 1, 2, 3, 4, 5. So first we've got like 9 qubits, right? So now like 3, 3. Yeah, another one. And so now we have 1, 2, 3, 4, 5. So 1, 2, 3, 4, and 5. We also have like 1, 6, and 7, and we have like 2, 8, and 9. So that's all we have. It's impossible to. Yeah, man. Yeah, that's going to be impossible to compare, at least by him. But essentially, if I'm adding a C naught between 1 and 2, so like a C naught, yeah, we'll just do this roughly, right? But it's the same as doing 1, 2, 3, 4, 5, 3, 4, 5, and then 1, 8, 9. That roughly looks like the same. You've got this pockets of squares in here. Yeah. How's this derived though? Like that's pretty nuts. Like that's actually proof. Ah, okay, so there's a proof. So without loss of generality, we assume that C naught acts on the first 2 qubits. We write a hypergraph state H in the expanded form of vertices 1 and 2 as follows. So I don't know why I understand this notation. So the C naught gate swaps these with these, alternatively equation 4.7 with 4.8. But these other parts invariant, therefore we obtain the following relations between the alt and the new hyperedges. So these equations show that only the hyperedges containing the control qubit can play a role. More precisely, shows that the new hyperedges that are added deleted are of the form Hmm. Okay, I don't understand. I don't understand this notation. The expanded form over vertices 1 and 2. Like, what is this expanded form? This I don't really understand. But I get it that these two are qubits 1 and 2, I guess, right? So this is, I don't know what it means, but like these times the hyperedge representing E00, which is, I don't know. I guess the rest of the hypergraph. Kind of falling asleep. Oh God. Gotta get something to drink. Be right back in a second. So, yeah. Mm. Still, this kind of feels like it's just possible because of the nature of these, of the states that these things represent, right? I think it's still worth digging into these at some point, but still want to know why. How does these? How is this proven? Can I search for this stuff? I can. Yeah, I can. But that's really the first time it appears, like in 195 pages. Like, how is that expanded form? Where is that defined? Like, hypergraph states. We call hypergraph state gain from state, blah, 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 blah. All three qubit hypergraph states with at least one hyperedge are local. Okay, so all three qubit hypergraph states with at least one hyperedge are local Pauli equivalent. Pauli X on a vertex I at all the hyperedges in the adjacency of I. A X respect to the hypergraph state in A and the state in B is obtained since the adjacency of vertex 3 on 2 X2 is applied. Finally, X1 is to all the three qubits. Here's the state in D. So hypergraph states also have an alternative definition using stabilizing formalism. However, the stabilization is not given by a tensor product of local operators. It turns out that even non-local stabilized description can be fruitful for investigating entanglement properties of hypergraph states. Given an Q hypergraph, state corresponds to hypergraph HVE. First, we introduce a term that can be regarded as a generalization of the term neighborhood from graph theory. We call it adjacency of a vertex and denoted by the elements of are sets of vertices which are adjacent to I via some hyperedge. So give an example, blah, 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 blah. Then for each vertex I, we can define the operator H consisting of the tensor product of all X and the vertex I, internalized control sets and adjacent beats. Then for each vertex sub I, we can define the operator HI consisting of the tensor product of Pauli X on the vertex I and generalized control Z gates on the adjacent qubits. Okay. These operator from a commutative group and the hypergraph state is their unique common eigenstate with eigenvalue plus 1. What the fuck? I don't know. Yeah, I think that is definitely a really interesting. These are preliminaries, by the way. Note that the vertex 1 is included in hyperedges, and therefore its adjacency contains an empty hyperedge. An empty hyperedge itself corresponds to a global sign -1, as in equation 2.75. For the sake of implementation, sometimes where it's clear, we will skip the tensor product brackets and commas and description of generalized controls in case instead write. Okay. So 27 local integer equivalents of 4 qubit hypergraph states with at least one hyperedge. It appears that the local Pauli operations are enough to distinguish these entanglement classes. dimensions. Okay, so what is this? Linear matrix pencil states. In this entanglement classification of tripartite pure states in non-homogeneous Hilbert space of local dimensions. Where eminent under slot transformations for so that there are two general multipartite entangled slot classes, W class and JZ class. Interestingly, the problem of slot classification of arbitrary M and N can be solved using mathematical structures of linear matrix pencils. What are linear matrix pencils? Okay, but that's not interesting for me right now. So you ever heard of matrix pencils? In linear algebra, if A0, A1, and AL are n by n complex matrices for some non-negative integer L, and AL it's not zero, the zero matrix, then the matrix pencil of degree L is the matrix valued function that defined under complex numbers the matrix pencil. So this is what the sum over all these matrices with a coefficient. A particular case is a linear matrix pencil. A linear matrix pencil A minus lambda B, where lambda belongs to the complex or the real, where A and B are complex or real. B. A pencil is called regular if there's at least one value of lambda such that the determinant is different than zero. We call eigenvalues of the matrix pencil all complex numbers. So it's a linear combination of matrices. So matrix pencils play an important role in numerical linear algebra. The problem of finding the eigenvalues of a pencil is called the generalized eigenvalue problem. The most popular algorithm for this task is the Qsaid algorithm, which is an implicit version of the Q algorithm to solve the associated eigenvalue problem without forming explicitly the matrix, B transposed B to the power of minus 1a, which could be impossible or ill conditioned if B is singular or non-real. Okay. But that's definitely not interesting. Okay, but I think I took the gist of the paper. No, but I didn't. In terms of, I don't know what that. I don't understand that notation though, and it doesn't seem to be defined anywhere. Where's that? Here. See proof in reference 32, but I oh, so there's an actual paper, because that's a thesis, so there's an actual paper about these. Oh, come on, dude, but that, like, These things are just in these papers. Okay, but I guess the oh yeah, actually, he's the author. That's cool. But it's pretty cool. I mean, it's definitely pretty cool. I just don't understand. Maybe it is explained here. What is these? Rewrite a hypergraph state as follows. So we have the hypergraph state. And I guess this is the 0, 0. But what is that? What does that mean? Where E0, 0 are E. What is E? I guess the edges, hyper edges, right? Such that their intersection with the control is empty, and the intersection with the target is empty. So, okay, so that means the hypergraph part of all the other. I don't know. It's a weird way of this just being multiplied. I don't know. And then 0, I don't understand why. Why would you? Why? How do you interpret this 0, 1 here? That's, I guess. I don't know, because then it's 0, 1, 1, 0. So for all those who are adjacent to the target, adjacent to control, but the intersection is empty. I think I'm too stupid to understand this. The C not in substance, but these other parts vary, and therefore we obtain the following. So I don't understand how they come to these. I don't understand how this is the representation of the hypergraph with these states multiplied by the rest of the hypergraph. I don't know what's the meaning of that, but I guess what they're trying to say here is that because of the C not only affects these and these here, right? it only affects the hyperedges that are part of the adjacency of the control and the control of the target. So these equations show that only the edges containing the control qubit can appear or disappear. More precisely, equation 13 shows that the new edges that are added deleted are the form. I don't think I fully understand that, but I'll probably come back to these. I mean, I will definitely come back to these. Okay. Man, it's already 1 hour gone by. Yeah, I don't know. You see, I need to still work that out, really. Because, you know, if I have this state and then another qubit with the same state, right? That's something that I would like to be equivalent to, like, you know, like these, right? 0, 0, 0, 1, 0, 1. Basically, oh God. But that's also not true. It's not that it's equivalent. It's just that's what's wrong. It cannot be equivalent. It cannot be equivalent because then I'm telling, that's the problem. That's the fucking problem, because then I'm telling that then the model is just inconsistent, because it's telling me that you know, these guys the same, like considering these being a mixture, and it's not. It's just fucking not. Like, that is the problem. That is the main problem that I'm having. That just makes no sense, because that so modeling the bell state like that also, like, no, it feels okay. I mean, that feels okay, because in a way this locally behaves like that, and this locally behaves like that as well, right? You know, how would I model these, how would I model these state? I would just say, you know, so 0 plus 1, 0 plus 1. But then at the end of the day, what I want is I want a way to define the system, define that entanglement, right? Ugh. But that it seems to be the only way. If I just kind of, really have these four options. 9, 1, 1, 0, 1, 1. But then let's say that has a weight. There's a weight to it. There's a weight to it that can doesn't matter where it belongs to. There's just a weight to it belongs to the system, right? 0.5. The rest is like 0.5, 0.5, 0.5. But I need to get so I want to get to a rule that kind of takes me here, and a rule that takes me here, like directly, while say I will apply the CX rule, right? And it would just leave me in the same state. Keep drawing things that look like fucking faces, man. Because the CX, CX would just just doesn't touch the state, right? So 0 plus 1, 0 plus 1. How can I derive these rules? Like, that's what I'm having a trouble with. Like, I don't know what is the formalism, or I don't know what's the tool set that I can use to kind of derive these graphical rules. But okay, that gives me some good examples of things that I could think about, right? The adjacency metrics, the adjacency sets and stuff like that, and well, let's put it this way, right? So following this pattern, it actually works, right? Because you're saying idly off the form. So the adjacency of target, but the adjacency of target is empty, right? So with these, so if you have these hypergraph, like that is just as a hypergraph state, that is just just two nodes. And so now the rule tells you, go look for the for the nodes that are adjacent to the target, and then connect them with a control node. But because there's no, then you don't do that. That's why it stays like that. And so I want to have something that sort of in a similar fashion goes and says, look, um, the thing is, the hypergraph states can make assumptions because they know that they so you know that that's the state that your nodes are in, right? Whereas here I cannot make these assumptions, but I could make a similar. I could just work on a similar idea, right, and say. So a control X here leaves me the same, while a control X here definitely leaves me somewhere else, right? This has got to do with, kind of adding hyperedges and whatnot based on the estates. Like the rule's gonna make reference to the fact that this is in superposition and that this is not. Because that's gonna tell you how many edges you need to create hyperedges. Complicated. But the base model makes sense. It's just I think the way the operations are mapped, it's not that trivial. And I'm just now realizing that not even the single qubit operations. Got to work on this a bit more. So this requires a bit of different shift. So that's not as simple as I cannot go. I cannot model the operations as simple like state replace replacing the states, because then I go away from my model space, and I want the model space to be just whenever there's a hyperedge, it means there's entanglement. Like there's no, I don't want models where, like these, yeah, that's the thing. So these cannot be part of my model state. Uh, Model space. That cannot be part of my model states because that's not entangled. But then I run the risk that, kind of these rules do not show the interference and do not show the things that I wanted them to show, like the actual phase keyback and whatnot. But yeah, okay, I mean, that would be another thing to think about, right? If you have these and you have phase keyback, right? So the fact that you have, that state, I want the CX to give me that state with phase kickback. And so I want to make sure the rule emphasizes that. Because the reason this happens is because it should create entanglement, but it doesn't. But the fact that it doesn't, it comes at a price. That's the point. The fact that there's no connection being created here kind of comes at a point, it comes at a cost. These rules should create and delete hyperedges, right? For example, if that's my state and I apply a CX gate, I should go back to this state, to this state. And I see that I cannot generalize. I cannot just say that's the method for any 2-qubit gate or any 3-qubit gate. I see that what I really have to do is kind of actually work pretty hard for each specific gate and actually have a specific transformation designed for each gate. Yeah, that's probably the way it is. I think that each transformation is going to be different. Right? So I want to translate these. So these are all, all different effects that you want to see with the CX, but then we need to come out with a rule that kind of, does that for the CX. But then, the Mulmazur gate is going to be another beast to implement, right? I think that's what I'm kind of getting at, I think. That the because essentially the generic stuff is just not, it just does not solve. It's just a wave function. It would just essentially be the wave function, and that's what I want to avoid. If I just keep representing those chunks and then just just pretending that these are just keeping track of the qubit stuff, but then essentially I end up with like hyper edges that have a bunch of combinations of these zeros and ones that don't really represent an entangled state, but I don't know that it doesn't represent an entangled state without actually doing the factorization, right? Which is already what you have to do with the wave function. How to do that? Cool. Anyway, yeah, that was a bit of a long stream. I think I should go get some sleep. Bye bye.